welcome to this video here. It's for anybody interested in buying or selling property in expensive communities in Mumbai, such as Powai, for example. Okay, we use something called the heat equation, which explains how property prices vary over time. So you notice that if there's heavy demand for property in one area, we can represent that with a bright red or bright orange color, and that represents high prices of property. And cooler areas have a lower color or a greener or a lighter color. These property prices have a nature to diffuse outwards over a space of time. And as we have discussed in previous videos, this can then enable you to make profits. So property values spread from high demand locations to nearby regions. The heat equation here given is del U by del T equals alpha nabla squared U, which is the Laplacian of U. So it's in fact just some kind of a Gaussian curvature on the space of U. U, of course, here is your property price, and alpha is the diffusion coefficient. So we have this graph over here for x, y, the location, and t being time. We also have price growth. So over time, the peak of this Gaussian here is going to diminish and it's going to get flatter and flatter. So the center drops in its maximum value of property price, and the property prices start to spread outward. And this idea can be used to actually make profits over periods of time. It can also, of course, be used to purchase cheap housing. If you know where the heated areas are, you just pick areas that are outside the heated area. Now, how do you calculate which areas are high in property value? There are a couple of models, in fact. There is something known as uh, the spatial recognition model. We use neighborhood features that makes use of latitudes and longitudes as well as nearest neighbor um, machine learning models. Um, these are further explained in our other videos, in fact. And using these modules, you can calculate hotspots with high levels of property prices. So from raw data to spatial features and models that reveal where the market is heating up next. You can implement this in Python, in fact, using your nearest neighbors model from using the pandas library and the sklearn um, library as well. And you can thereby create a heat map of a city. In fact, if you know what the nearest metros are, metros, in fact, metro or rather metro lines will help to will in fact raise the price of a property. The proximity to metro lines or transport will raise the price of a property because that property is generally going to have a higher demand. Um, so if you're clever, you can pick properties that are further away from your metro lines, and these problems can get quite mathematically involved. In fact, we'll analyze them in future videos. You can detect future hotspots as well using this model. Areas surrounded by high growth neighborhoods are more likely to become the next hotspot. And you can predict appreciation using current price, neighbor average price, heat index, metro distance, school distance, population density, and each of these similar metrics. We'll have videos discussing each of these ideas. In fact, it uses a model called the XG boost regression. This is something that we're also going to investigate going further now. You have graph-based heat diffusion as well. This is a little different from normal Gaussian heat distribution where you have the Laplacian. This is more discrete. This is pulling in ideas from discrete mathematics. We're going to go ahead and investigate each of these ideas separately and see how best you can use it to predict cheap housing in expensive neighborhoods. Um, and you have P, your vector of neighborhood prices, L is your graph Laplacian, and X is your economic infrastructure factors. So model the city as a graph and simulate how prices diffuse over the network of connected neighborhoods. Of course, there are a few limitations to this model here. There are data quality issues, irregular market shocks, policy and regulatory changes, human behavior is complex, and of course, not all factors are measurable. But of course, we can do the best we can with mathematics, and we can get quite close to our desired approximations, in fact. All right. So I think then that brings us to the end of this video. In fact, let me just get here to the code. All right, give me a second, please. Yeah. Now this model here, I'll just describe very briefly how the KD tree search works. In fact, it's an algorithm to calculate the nearest metro station to any given point. So your metro stations can be described in terms of latitudes and longitudes, and you have a point P with coordinates given here 19.07 and 72.87, and then you can find the nearest points to this nearest metro stations to this point. All right, you have these equations. So in fact, you start with the top of the metro on the northernmost point, so S1, and then look at the two closest metros to it. That is south west and southeast, and you have S2 and S3. Now just find which one of them is in fact closer to so rather, I should say, in fact, conversely, it should be southeast and southwest, and find which one is closer to P. So of course, here it is S2, which is closer. So then you then branch off and you move on again to the next level. Find the two closest to S2, the two closest metros to S2. Again, southwards, not northwards. We're going southwards always. So you have S4 and S5. Now, which one's closer to P? Of course, it's S4. And then you you see that in fact S4 is the closest. There isn't really anything else closer, because if you again proceed to S6 and S5 like you normally would, you'll quickly realize that S5 is just further away and S6 is also further away. So S4 is the best candidate, and you'll have to eliminate other possibilities from the branches of S3 as well. But that's really not so hard, because S3 shares the same no same points S4 and S6. And again, the branch for S3 would again lead to S4. So this it's a very fast algorithm, in fact, known as the you use the Haversine real world accuracy formula, distance formula, and you can use it to solve the KD tree algorithm in O of log n, in fact, and this makes it a very efficient algorithm to actually calculate the nearest metro. So we'll discuss each of these points in further detail, in fact, going forward. And I thank you so much for watching in and tuning into this video. All the best in your hunt for cheap housing, and I'm signing off for now. Best.